The goal of this video is to understand tangent slopes of parametric curves. So the plan is to quickly review parametric curves, derive the formula for the tangent slope of such a curve. We're going to examine several explicit examples. We're going to understand how the tangent slope formula might break down, and we're going to figure out how to use such breakdowns to understand the behavior of the curve. Suppose you wanted to keep track of the motion of a bug on a tabletop. So it's going to move around for a while, and what you'd like to do is keep track of its path. So what's the mechanism we need to do such a thing? Well, first of all, we're probably going to want to mark the x and y axis on the tabletop, so we have some coordinates to record the position. And we could call these x and y, these directions, and we're going to need another variable, a time input, to describe when the bug is where. So at time 0, we have some coordinates, and then we move along and perhaps find another time, record the coordinates there, find another time, record the coordinates there, and so on. And eventually you will collect all this information together, and you should have a decent record of how the bug traveled around on the tabletop. Now you'll notice that what we have here, what we need both the x and y coordinates to be functions of t. In other words, we want a pair of good old-fashioned functions of one variable. And when you have this collection of data, you have what is called a parametric curve. So x and y are both going to be functions of an input variable t, which it is often convenient to think of as time. So here's a particle traveling in the plane, and it's going to make this little loop-de-loop here. And for this path, we can break out both the x and y functions as functions of the input time t. So let's label our axes x and y. And we will graph here, in the first instance, the y coordinate as a function of time. And we'd also like to plot the x function as the x coordinate as a function of time. But it's going to be convenient, for reasons that should become clear in a moment, to graph this slightly differently. So what we're going to do is we're going to reverse the role of the horizontal and vertical axes here. And we're going to use the vertical axis to plot the independent variable t and the horizontal axis to plot the output variable x. And we're going to place this here under our parametric curve. And now we're going to watch as time advances over the interval of its domain. You can see how the x and y coordinates are tracking on the curve as a function of the time t. Now it's convenient to be able to interpret the graphs of y and x respectively as functions of t and understand what aspects of these graphs have to say about the parametric curve. So for example, if you can see that the y function is decreasing as a function of t, then for those same times you know that the parametric curve is moving down. And of course, if y is increasing, then you know that the particle is moving upwards in the parametric curve. And similarly, if x is increasing, so if you can find intervals of time for which the function x is increasing, those times are going to correspond to times when the particle is moving to the right. And when x is decreasing, then those times are going to correspond to times when the particle is moving to the left. Now we want to make one other distinction here. A parametric curve is not just the graph you get. So here is the path of, well, you might think one parametric curve, but actually infinitely many parametric curves. And let's just keep track of 4 of them. So we're going to plot 4 parametric curves. Now watch what happens. They're all going to trace out the same piece of graph, and yet you have 4 different parametric curves. So I'll make a distinction between the trace of a parametric curve, which is simply the leftover trail that a parametric curve leaves behind, and the curve itself, which conveys more than that information. It conveys how the particle travels along the trace. So just keep this in mind. Here we had 4 different curves, but only 1 trace. So let's get to some calculus. Suppose we have parametric curves. So we're keeping track of the motion of a particle in the plane. And for the rest of this discussion, we're actually going to assume that both coordinate functions are continuously differentiable for all time in the domain of the curve. In other words, x and y both have derivatives, and those derivatives are continuous functions. This is going to simplify our discussion. And we just aren't going to get into the pathologies that occur when you take sort of piecewise differentiable functions and piece them together. That should be the subject of a whole different video. So for this video, we're just going to assume that both coordinate functions are continuously differentiable in the domain. Now, we're going to pick a particular moment, say t0, and we'll find the position on the curve at that time. And what we'd like to figure out is the slope of the line tangent to the curve at that point. In other words, what is dy dx when t equals t0? Before we start to understand how to answer this question, we're just going to notice that generally the trace of a parametric curve does not exhibit y as a function of x. And that's going to be inconvenient for what we're about to do. So we'd like to zoom in on this picture to guarantee that happens. So we're just going to take a little piece of curve here and blow it up, and then we're going to notice that basically this little piece of curve passes the horizontal line test, or passes the vertical line test, I should say. It's sort of the graph of, it's exhibiting y as a function of x. Let's actually sort of justify why we know we can do this. So let's assume that x prime of t0 is not 0. Now there are a couple ways it could not be 0. One way is that it's positive. Now remember, our hypothesis is that x prime is actually a continuous function. So under these circumstances, if we were to plot dx dt as a function of time, at t0 the function value is positive, and we should be able to find a little interval around which the derivative remains positive. This is because the derivative is a continuous function. And if that's true, that means throughout this time interval, x is going to be increasing. And so if we keep track of the particle on the plane, it means throughout that time interval, the particle should be moving strictly left to right. Great. Now the other way that x prime of t0 could not be 0 is if it were negative. And the whole argument can be repeated now. So the value of the derivative at t0 is negative, and we should be able to find an interval around which dx dt is always negative. And that would mean that there should be a time interval in which x is a decreasing function, and that means if we kept track of the particle, it would be moving strictly right to left. So what's the upshot of this? The upshot of this is, either way, the assumption that the derivative is not 0 has guaranteed that we should be able to find a small time interval during which the trace of the graph exhibits y as a function of x. So in other words, this little bit of graph is going to pass the vertical line test. This is going to be useful conceptually for what we're about to do. So we have a parametric curve, and first of all, the first equation tells us that x, of course, is a function of t. And by restricting our domain sufficiently, we can now regard y as a function of x. And of course, the second equation of the parametric curve tells us that y is a function of t as well. What is this picture we've got? We've got a classic composition. So we compose x as a function of t with y as a function of x, and that should get us y as a function of t. Now, we want to do some calculus. We want to take derivatives. And in the context of a composition, the proper way to go about this is, of course, the chain rule. So dy dt should be dy dx times dx dt. Classic chain rule written in terms of Leibniz notation. And of course, we can just then solve for dy dx. dy dx should be the quotient of dy dt divided by dx dt. Now, word of warning, this isn't really a proof that the derivative exists. But what it does do is it tells you that if the derivative exists, this has to be the formula. Because, of course, if dy dx exists, if y is a differentiable function of x, the chain rule tells us it has to obey this relationship. So we're leaving aside the proof of existence, but this is a pretty compelling argument that dy dx really should be dy dt divided by dx dt. And if you like Lagrange notation better, you could write it dy dx evaluated at t equals y prime of t divided by x prime of t. That should tell us this slope of the tangent at the time t naught. So let's look at this formula a little bit. You could imagine doing some, quote, algebra to this, I guess, and divide the dt's. Now that's a useful mnemonic device that might help you remember this formula. But if you imagine that somehow this constitutes a proof, you should be horrified and not think that way. So this is not a proof that dy dx is the thing you think it is here. So this is not a legitimate proof, But as I say, if it's a mnemonic that helps you remember the formula, that's great. Let's take a look at an example. So here's x equals t cubed minus 4t, y equals t squared minus 2. And this gives us a loop-de-loop. And our job is to find the equation of the tangent line at t equals -1. So the first thing we better do is figure out where the point is at t equals -1. So substitute -1 into the x function, we get 3. Substitute -1 into the y function, we get -1. So what are we talking about? We're talking about the point 3, -1. That's the position of the particle at time t equals -1. Now we need to find the tangent slope. According to our formula, dy dx should be the quotient of dy dt by dx dt. dy dt is simply 2t, and dx dt is derivative of a cubic, 3t squared minus 4. That formula is apparently giving us the tangent slope at various times t. Let's plug in -1. Carefully evaluate this expression. You get 2. The tangent slope should be 2. Now, if we draw this line with slope 2 here that goes through the point 3, -1, this picture looks awfully good. It looks like we really have figured out the tangent line, and the equation for this using point slope form is very simple. And there we go, our first application of the tangent slope formula. It seems to be working. Example B, find dy dx for the parametric curve x equals cosine t, y equals sine t. We'll restrict t here to be in the closed interval from 0 to 2 pi. Now, what's the trace of this curve? If we square x and square y and add these together, we'll notice that x squared plus y squared is equal to cosine squared t plus sine squared t, which of course is always equal to 1 no matter what value t has. So what do we know? We know that this particle lies completely, the trace of the particle lies completely in the circle x squared plus y squared equals 1. In other words, it's the unit circle. So the trace lives somewhere in the unit circle, and actually we can say more than this. We know that the trace is going to wind up being the whole unit circle. Why do we know that? Well, it's convenient to think of t not just as time in this example, but we can think of t also as an angle. So if we imagine that t represents a radian measure of an angle swept out from the positive x-axis, then we know from our understanding of wrapping functions that the coordinates of this point are exactly cosine t sine t. Now you can use your favorite graphing utility to bear this out. I use Desmos, and you can watch the unit circle get swept out here as a function of t as t runs from 0 to 2 pi. Now we want to find dy dx at any particular t, and our formula tells us that in this case we should get cosine t over negative sine t, which we could write as negative cotangent t. But for reasons that'll become clear in a moment, let's write this as -1 over tangent t. And we're going to take a look at the picture on the left, and we'll notice that for that angle, the horizontal component here has length cosine t, and the vertical component has length sine t. And if we take that ratio of sine t to cosine t, we'll get the slope of the line running right through the origin there, containing that radial segment. So that slope is tangent t, sine over cosine. And we know that the tangent of at the circle there at that point is going to be perpendicular to this. It's going to be this line right here. That's the tangent line. And so that slope should be the negative reciprocal of tangent t. In other words, it's -1 over tan t. So our formula certainly looks good in this example. It seems to be doing the job. Let's take a closer look at what happens when we substitute pi into this formula. There's a little bit of a problem because sine pi is 0, and so the formula breaks down. Well, what happens when t equals pi? It's pretty clear in this picture that the tangent line is vertical. And it makes sense that the formula for dy dx should be undefined because a vertical line has an undefined slope. And so the fact that the formula breaks down seems to be quite natural in this case. But it does lead us to the general question, what does happen when dx dt is 0? How are we supposed to handle such a case? When dx dt is 0, the formula for the tangent slope breaks down because we will be attempting to divide by 0. So the general question here is, what can we conclude about the tangent line in such a situation? Now, a reminder, we've assumed that both x and y are continuously differentiable for all t, and we're going to use that fact throughout. So we're going to take case 1. We're going to assume that dx dt is 0 and simultaneously dy dt is not 0. Now, what we'll think of here, usually we like to plot the dependent variable along the vertical axis. So for example, if we had a function f, we'd like to plot y equals f of x. And the fact that it's a function, the graph of a function, means we'd be passing the vertical line test. And this is the way we usually look at functions. And by the way, if we were looking at tangent slopes in this context, we'd calculate rise over run. Rise would be a change in the vertical component. Run would be a change in the horizontal component, and so our tangent slope, we'd want to take dy dx, the derivative of y with respect to x, and if we were working with a parametric curve, we've seen that should be dy dt over dx dt. But you can imagine, just like there are parts of the world that drive on the right side and parts of the world that drive on the left side, you can imagine that for whatever reason, in fact we had a reason earlier in this very video, you might want to plot the independent variable along the vertical axis and the dependent variable along the y-axis. And so if you did that, you might want to plot a function x equals f of y. Now, if you're going to look at it this way, you're going to have to tilt your head. And if you were to calculate a slope in this context, then your rise and your run would actually switch roles. And in this case, you're really talking about dx dy as the relevant thing to calculate. And the amusing thing is the arguments we made earlier still apply in this case. You'll find that the value of dx dy should be, in fact, dx dt over dy dt. It's the reciprocal of the expression we had before. Why is this all useful? Well, it's going to help us interpret what happens when we're looking at a curve and we see dx dt to be 0. Well, the tilted observer would see this as an indication of what they want to say is that their idea of tangent slope is 0. In other words, they have a horizontal slope. But a horizontal slope to the tilted observer is exactly the vertical slope to us. So what we're going to be able to conclude is there's actually a vertical tangent line. So let's revisit our example. At t equals pi, dy dt is -1, dx dt is 0. That's a non-zero dy dt over a 0 dx dt, and we're going to interpret that to mean that we have a vertical tangent line. Just for fun, let's visit the case t equals pi over 2, because in this case, dy dt is 0, dx dt is -1. This is a case of a 0 over non-zero ratio, and there's no drama here. This is a horizontal tangent line. But I only point this out because you should see the symmetry here between the tilted and non-tilted observers. Exchanging the roles of x and y is like reciprocating your expressions for the slope, and that's like flipping your graph across the line y equals x. So there's a certain symmetry here that if you're willing to understand how a 0 over non-zero ratio gives you a horizontal tangent line, then you should be willing to believe that a non-zero over 0 form gives you a vertical tangent line. Now let's look at case 2. This is the case where dx dt is 0 and dy dt is 0. And in this case, here be dragons. So some unpredictable behavior can occur in this case. And let's imagine why. So we're trying to evaluate dy dx at t naught. And we look at this ratio of derivatives. And we can think of that as a ratio of limits here, because a derivative is just a limit of secant slopes. And you'll notice that if both of these limits are 0, then what does this look like? This really resembles the classic 0 over 0 indeterminate form for a limit of a ratio. Mind you, we're not trying to evaluate the limit of a ratio. This is a ratio of limits. However, this is suggestive because what it might imply is that perhaps anything is actually possible here. This could be a truly indeterminate situation. In fact, what we're going to do is we're going to show that when the parametric formula for dy dx yields a 0 over 0 form, then it is possible that the tangent slope of the trace actually exists, the tangent line of the trace is vertical, or the tangent slope of the trace does not exist. So in other words, anything really is possible when your formula gives a 0 over 0 form. So let's start with this simple example, x equals t cubed, y equals t cubed. This pretty clearly parameterizes the line y equals x. Why? Because x and y are quite visibly equal to each other, and as t ranges over all real numbers, you'll notice that the value of x and y go from being, very negative to very positive. We seem to be sweeping out the line y equals x. All right, well, if that's the case, we might expect dy dx to be 1 for all t. And it's very close to being the case, but look what happens. Both the derivative of y and x with respect to t is 3t squared. So this ratio, 3t squared over 3t squared, you can cancel the 3's safely, but we're going to be very careful about this, very pedantic actually. We're not going to cancel the t's because one of the possibilities is that t equals 0, and you can't divide through by 0. So what does this mean? This means this quantity is undefined when t equals 0. By the way, it's pretty clear that it's equal to 1 anywhere else, just like we expected, but the bigger point here is it really is undefined when t equals 0. Now, when t equals 0, both x and y are 0, so whatever bad thing is happening must be happening at the origin. So what's going on at the origin? Let's take a look at the actual curve in action. This is Desmos again, and you can see as you watch it sweep out, there's this moment, apparently t equals 0, where the particle seems to come to rest. It sort of hesitates at the origin before it moves on. Apparently, this is causing the trouble. So what could be going on? Well, really the language we need is the language of vectors. So pardon me, we're going to have to talk about vectors on this slide and this slide only, but if we're looking for this tangent line, if we're trying to understand the slope of this tangent line, well, the velocity vector, whose components are precisely the derivative of x and y with respect to t, that velocity vector lies along the tangent line. And indeed, you can see now that the slope of this line is the ratio dy dt over dx dt. It makes perfect sense. But what happens if that velocity goes to 0? In other words, what happens if the particle happens to pause momentarily at that time t equals 0? If the vector goes to 0, then there's nothing left to hang your hat on. The ability to calculate a slope from this kind of scenario, it's impossible. So when you have a parameterization where the instantaneous velocity is 0 at a particular moment, then you lose the ability to analyze the tangent line and the tangent slope. And in fact, that behavior, when the velocity goes to 0 momentarily, can hide any kind of underlying behavior of the trace of the curve. So maybe a tangent slope should exist, maybe the tangent line should be vertical, maybe there's no tangent line to be found at all, as we shall see in the next two examples. Example D, we have x equals t to the 9th and y equals t cubed. And you can work out the algebra, and you can you take the cube root of x to get y. So this we expect to parameterize the curve y equals x to the 1/3. And if we watch Desmos trace out the curve, we can see that indeed we get the curve y equals cube root of x, but we'll notice the hesitation. dx dt is 9t to the 8, dy dt is 3t squared, and the ratio is this quantity. And you'll notice that once again, this is undefined when t equals 0. And as we expect, when t equals 0, x is 0, y equals 0, we saw in the picture there's something funny going on at the origin. This is a moment when the instantaneous velocity is 0. And so we lose the ability to find a tangent slope at this point. Now, if we analyze the trace directly, we know that y equals x to the 1/3. dy dx is 1/3 x to the negative 2/3 by the power rule. This function we get is not defined when x equals 0. So in this case, the momentary hesitation at the origin is actually masking a vertical tangent line. Let's turn to our final example, x equals t cubed, y equals absolute value of t cubed. Now it's pretty clear that this should parameterize some part of the curve y equals absolute value of x. And if we watch Desmos in action, we will see that there is a slight hesitation at the origin. And this is going to be backed up by our calculations. So dx dt is clearly 3t squared. dy dt, let's leave this as an exercise, but you get a piecewise defined formula for this. To the left of the origin, the formula is negative 3t squared. To the right of the origin, the formula is 3t squared for the derivative. And you'll notice there's an ambiguity at the origin because we could actually decide to let 0 fit into either one of these parts of the formula. So you could decide to have this as your formula for dy dt. This is a perfectly legitimate piecewise defined formula for the derivative. So we have these two choices. And what's amusing about this then is we have an undefined tangent slope, which even comes with its own ambiguity. So you can either have a minus sign in front or a positive sign in front. But in either case, this is an undefined quantity when t equals 0. And we'll notice that t equals 0 corresponds to the origin, and there's no tangent slope at the origin. So in this case, the momentary hesitation's masking a sort of calamity in terms of tangent slopes. Turns out there's not a tangent slope to be found anyway. Now, you may have been looking at these examples, and you may have thought to yourself, well, you're throwing away a lot of information because you're not actually trying very hard to figure out the behavior of the curve when t equals 0. And indeed, whenever you have an indeterminate form in a situation like this, it may still be possible to recover information about the tangent line by examining the limiting value of dy dx as t approaches t naught. So let's just revisit these examples quickly. When we had this expression for dy dx, we were careful not to cancel out t's, but of course you could cancel out the t's, and that formula would still be good for all t other than 0. So dy dx has this nice simplified formula everywhere except for 0, and then what we can do is we can imagine the form that this function takes, and we can see that as t approaches 0, the limiting value of this expression is infinity. So what's going on here is we should be able to look at the value of the tangent slope nearby and let it approach the trouble spot, in this case t equals 0, and we can see from the limiting behavior that gives us an inkling that the tangent line at the origin really should be vertical. A similar argument can apply in the case of example E. So when we calculate the expression for dy dx as the quotient, we get a nice slick ratio of -1 when t is less than 0 and 1 if t is greater than 0. So once again, we can analyze this function in terms of t, and we see that the limiting value as we approach from one side is 1, and the limiting value as we approach from the other side is -1, which tells us that the limiting value does not exist. That's a strong hint that the tangent slope when t equals 0 fails to exist.